Thank you. But yeah, by the way, I've learned both now, so I know how to swim and I can surf as well. All right. So yeah, quick intro, as Adam said, lead data engineer at ThoughtWorks Australia, and started off in backend engineering, working on JVM languages before I moved on to data and machine learning. And I'm going to talk about parallelizing Spark data pipelines using ZIO. So before we get into the details, let me quickly cover a little bit of the problem context, like why was even parallelization needed? And what do we even mean by parallelization? Because you might be thinking, Spark is already a distributed language. Why is there need to parallelize? But I'll touch upon that aspect which is missing in Spark. So just to cover up the business case, why there was a need to do that. So this data pipeline that I'm referring to here was responsible for producing some critical business metrics and business metrics which were required to be produced by a certain time of the week or certain day of the week so that the stakeholders can take certain decisions such as, and this is in the context of a retail data or retail ecosystem, so product pricing, what products to bundle together, put on promotions and things like that. An example of that metric could be, let's say a product lost sales in a certain week. You would want to know why that happened so that you can then take a better decision in terms of pricing or putting in a promotion at a certain time. So a metric that can explain that better could be maybe there was a substitute product in that same week which gained a lot of sales, and that tells a part of the story, and then you kind of figure it out, and there could be such more metrics. So these are the metrics we are talking about here. Another challenge that we had was we did not have control on the data set availability. And what I mean by that is normally in data pipelines, you start off by source data which you operate on. We did not have an influence or basically a way to do that ingestion of the data earlier and then start the process ahead of time and then spend like 2-3 days of running a long-running Spark job and finishing it like that. The other challenge was in terms of the compute infrastructure, it was a giant, massive shared cluster, which was shared across the company, across various teams, and every team would have an allocation on the cluster, and they had to basically stay within the bound of that. You could tweak it a little bit. You could bump up your compute for a certain time when you needed to, but it wasn't really feasible to have, let's say, half of the cluster for one team for running your workload, which made it harder as well. And we are talking about just the last point there is about the scale of the data set. So we are talking about terabyte scale to start with, which then with join operations would explode further. And you're basically dealing with a lot of billion rows of data at any given of time. So a classic batch Spark processing pipeline is the context here. So hopefully this gives you an idea that you basically have a very strict window to operate on, and the deadline is for producing these metrics was fixed. You couldn't really change that because after that, if you deliver the metric, there won't be any use of doing that. So quickly, at a very oversimplified diagram of a data pipeline, for people who don't know what data pipeline is, essentially you have a source system or from where or some sort of data source where you start with, and on the far right you basically have a target where you write the data to, and in the middle you have a computation engine, which can be Spark or something else. We are talking about Spark here in this context, which would perform operations such as map, filter, aggregation, and so forth. Probably you're seeing this diagram twice today. There was another talk on Spark which covered this diagram. But it's important to sort of touch upon this to be able to articulate the need for parallelization. So Spark typically is comprised of a driver, worker nodes where you start your executors, which are independent JVM processes, working on a certain partition of your data. And then there's a cluster manager in the middle, which coordinates the communication between driver and these executor nodes. So all this is good. Your tasks are performed in a parallel manner on a certain part of your data, and then all of the tasks finish, they get combined back, and then you finish your job at that point. However, the operations that, if you typically see a Spark application, we are talking about jobs, stages, and tasks. So these jobs are not really submitted in an asynchronous manner. They are submitted one by one. Once a job is submitted, that is being computed in a distributed manner, but not the jobs themselves. So across these jobs, the driver submits them one by one. So there's no good reason for the driver to kind of distribute them, even if there was a good reason to do that. Even if these jobs were sort of very independent from each other, driver would not really submit them in an async manner. Now, on this slide, I want to talk about knowing how Spark works, very specifically how our data processing pipeline needs were. So if you see on the diagram, you would notice like there are 3 blocks that I've shown there, essentially to show we are dealing with mainly transactional data or transactions that customers have made in a retail store, let's say. And they were like quite independent. So they were about 36 different transaction source data from different places, which went through the same sort of processing pipeline where you read the transactions, you'll perform metric computation, and you'll write it to a target storage. Pretty simple. But then the important point here is that you are doing the same set of operations at an abstraction level, same sort of metrics that are being computed. There's not really anything different going on. But if you use your vanilla Spark in a way that Spark behaves, you would end up processing them one at a time, even if clearly you can see there's no reason to do that one at a time, right? So you have independent data sets. The output of one processing pipeline does not determine what next pipeline would do. They're absolutely decoupled. So there's a big opportunity here to parallelize. So knowing all this, how Spark works, where this opportunity was, let's talk about ZIO now. So there have a lot of talks already been done, which have covered about ZIO's asynchronous features and things like that. Maybe there's an open question around ZIO versus future, like why would you even need ZIO into the picture? Why not just natively use future, which is already there with Scala? That could be a separate talk in itself, but just on a high level, I think the key features of ZIO were basically winner between the two in terms of the concept of fibers, which are lightweight threads, the fine-grained control, the predictability, all the functional APIs, very less amount of code that you have to write for a lot of things, which I'll show in some of the examples later. So those were the key callouts, which is why we sort of chose ZIO as an option to parallelize and fill that missing gap. So some of the notable features of ZIO that we ended up using in the pipeline were for each par, for can join, which were the two main features which allowed us the parallelization at a job level. The second feature was around combinators, mainly for interop between monads, so such as try or either, and then you can have same effect. All of these different types can be then used with ZIO wrappers to convert into ZIO effect, and then you can nicely bake them into a for comprehension. And then finally, the retries and timeouts, which is one of the talks that has already covered quite a bit around failure management with that. So on the second point, and I'll show you examples for each of these, I think the second point around combinators was a big win for us because we had a lot of code libraries which was shared across the organization, and a lot of people would contribute to that with the shared ownership. And all the typical common operations that you find in data pipelines, a lot of IO-related operations and so forth, they were all already available as core library functions. Now, if we didn't have this option of interop, and we wanted to use ZIO, it would have made it very hard, and we would have ended up duplicating a lot of code. We didn't have to do that because of this feature. So just to show quickly, examples of each, like some code snippets to explain these points. So this is a for each par example. which basically shows you how you can run your transformations. So pipelines to run assume that they are a sequence of tasks of type A. Type A in our context would be typically datasets, a Spark dataset, which is basically a table representation of your rows and columns of something, or a dataset that represents a transformation with some metrics that have been computed from the original dataset that you started with. So these are like all the different parts of your code in the pipeline, which return something, which perform certain computations and return a data set back. And you have got a sequence of those as task effects. Now, you want them to be run in parallel. So the parallelism factor that I've passed on to the permits value here is essentially to control how much you want to parallelize. Because this is also quite important to know. You can't go crazy when parallelizing, because you also have to respect what amount of compute you have at your disposal. Because normally, when you have a cluster manager, it also comes with certain constraints, like, and especially when it's shared and you have a concept of compute allocation. If you exceed your capacity, your job may be your job may get into a bursting state and then finally get killed, and you have essentially lost money on all that compute that has happened till that point of time. So it's also important to remember what is the right level of parallelism that you want to drive your code with. And then for each par, I think a lot of examples earlier in the talks have already covered that. And then finally, once you run these, you basically get back results, all results in the code, which is nothing but a list of result. A result could be your own data type that you can create based on your business need. It could represent, from the list of models or data sets that you have been working with, which of them has passed, which of them have failed, and so forth. So this was pretty much the most important feature that gave us this uplift of parallelization, or almost like the driver code for all of this. The next example is around fork and join. Now, fork and join gave us an additional level of parallelism and optimization. And where did that help us was around a lot of I/O read operations. So it is very common to read a lot of different data sets when you're operating in a data pipeline, where you would read a lot of these Parquet files, for example, and then once you've read all of them, you perform certain operations, which are like transformations, and then you write it somewhere, right? Very general sort of flow. But there is no reason to read all these files one at a time, once again, right? If you have, let's say, 5 or 6 of these, I've shown like 2 very basic, like 2 data sets here, but normally you may have much more than that. So there's no need to read them one at a time. You can actually like run asynchronously, read them together, read them in different fibers, and then join them back, which is what I'm showing there. So you start off with 0.fromTry. You have a repository.read, which assume is a library available to you, gives you a read behavior. And notice the .fork in the end. As soon as you do that, it runs a new fiber, gives you back asynchronous first task, second task, and then you do a join on each of them to make sure that you get the result back from those fibers once they have completed. And then you perform a score, which is assume a scoring sort of function in your data pipeline, which then uses all of these data sets together, and then you log the result back, and then you finish it off, right? And then finally, retries and timeout was another feature that we used. It is common to see certain parts of your code where something can be slow running or error prone, and just with another retry it passes. So we had a case where we had a SQL table from which we had to return some results, and it was sometimes a slow running query where you don't want to wait for too long, and you might have to run it twice, and then the second attempt you get the result back. So this was a case that we had where we basically baked them with a retry policy of recurs2, exponential backoff, which was again covered in a talk today, and then finally with a timeout where you're saying that try this 2 times every retry with the exponential backoff of 2 milliseconds, and then finally fail it in 10 minutes if it doesn't finish within that time. So the key thing here is that it was quite easy to create a retry policy, and it's quite a bit going on here, but it was very easy to do that in just a few lines of code. Now, a little bit of segue from ZIO and parallelization to some of the functional Scala features. Now, typically in Spark, if you use the Scala API, only then you get a data set which is a type-safe representation of a data frame. So we use that a lot. And basically, a data set of A here in this context means A is typically an entity from your domain model, so like customer, product, transaction, and so forth. So by using that, all the function arguments across our pipelines were type-safe. Essentially, you will get a data class. I mean, if you do a data set of dataset.map, you get a case class, which is a row from your data. And because it's a Scala case class, you get all the benefits of using Scala operations on those. You know what columns are there. You know what types are there. So all the type safety benefits, which we have been speaking about all this way. And then finally, besides dataset, it's also common to use a lot of ADTs in data pipelines, where it's basically a data structure which represents something, some sort of concept in your pipeline. And instead of having them as strings or unsafe sort of data types, we ended up using a lot of type-safe ADTs. So essentially now you have type-safe data sets, you have type-safe ADTs, and then I have not mentioned that here, but I'll briefly mention that even our config layer was type-safe. We use Circe for a lot of data modeling and also for reading the config values. Another inspiration from FP was to use small functions. So it is pretty common in a data pipeline context to create transformations. So you start off with data set, and then you end up with data set until you write it with an IO operation. So it is tempting to write a 100-line function, and then once you have a bug in that metric, then scratch your head and trying to figure out like where something went wrong. Instead of that, you could always break it down into small functions. So let's say you have a transformation which is quite complex. There's a lot of windowing operation and whatnot, and a lot of aggregated metrics being computed. You can break it down into a series of small steps. And each of those steps is a small unit of transformation, which you can then write and test it really, really well for what it's doing. And that transformation does not need to know about any other transformation that will come later on, right? So you could break the whole thing in that in that way. And then you can keep piping the data set from one to the other, and then to the other, and then you basically kind of create a chain of functions. What is the advantage of this? Reduces the cognitive load, makes it readable, the whole code readable, and you basically can onboard developers easily. Most importantly, if you have bug in a metric, you can easily figure it out in a rational manner by seeing, if I have 10 functions to do this computation, and each of them is working fine, then it should be fine, unless you have missed a test. Or you could clearly say that, okay, this third function here is not doing its job correctly, and you can just focus on that. And there's another benefit to it, which I'll talk later in the later slides. And function currying, as I've put there as another feature that we leveraged a lot for achieving this sort of function chaining or piping behavior. And that example over there, get metrics for target hierarchy, is showing that to you, where get active targets is, let's say, a function that takes a data set of a product, filters down and gives you all the active products, which the next function, which is metrics for target level, has no idea about, and it doesn't need to know, right? All it knows is it will get an active list of products, and it will basically operate on that and then do its job. Now, something that I want to point out here is that the pipe operator that I showed in that example is not really something that Scala offers out of the box. It was something we wrote as an inspiration from F#, purely from a readability perspective. It does not do anything very crazy. All it does is it takes a type of a value of type A, and it's an infix operator exposed as a function, applies F onto X, and returns a value. And all it does is basically, in our context, takes a data set, performs transformation, passes it on to the next. So data set to data set to data set. All right, so all that is good. And when we look back, there are some of the lessons that we learned because we did a lot of concurrency or asynchronous sort of behavior on top of Spark. So we had to kind of cater to some of the side effects that came with it. So one is that normally, if you work with Spark, there's a feature called caching, where you can actually do a .persist call on a data set. And what it does is it essentially performs that computation, and anywhere where you refer to that computation downstream in your code, it does not do it again and again, right? So you typically pick out something that is very common and used in various parts of your code and cache it. Now, because we are running things asynchronously, which Spark does not know about, it would do that caching again and again, and we'll end up using a lot of memory on executors and getting out-of-memory errors. How did we solve it? By using an in-memory cache custom implementation, by essentially creating like a memoization behavior, where you put a key and a value and make that shared across your jobs so that each job sort of knows if there is already a key for it, don't compute it again and again. The other lesson that we learned was almost towards the end of it, we realized that there is a further optimization that we can do, which is about differing levels of parallelism in that code snippet that I showed you earlier. So you could actually see in your data pipelines that there are some parts of the code which are less compute heavy, and there are some parts which are more compute heavy. So you can take advantage of that and bump down your parallelization level so that you can get the most out of the parallelization. So for example, in our case, all the aggregation-related stuff, we sort of bumped it down because that used to take time. And anything after aggregation, such as scoring, we sort of bumped it up. And this is something I came to know like quite recently, which is about ZPark.io. There's some sort of work happening in this area, so I'm not sure how mature it is to use as of now, but there is work to basically bring ZIO and Spark together as a framework where you can bootstrap your entire Spark application with ZIO and reduce even further boilerplate code. But my frank opinion, I did not find it hard to use ZIO on Spark as is. But yeah, that's something to be aware of. And finally, to conclude, most importantly, ZIO helped us achieve our SLAs. We were able to deliver the metrics on time and sort of get to a point which was the whole point, right? Like why we were even parallelizing to achieve this outcome, and we achieved that. But besides that, like looking at hindsight, I realized that compute is costly even today. Even if storage is cheap, compute isn't. So consider using parallelization as much as possible so that you can get the last drop of juice from your compute resources and use it at the fullest capacity. So it does not have to be a hard deadline and a need for parallelization. You could even use it otherwise so that you can leverage your compute to the best possible outcome. Another thing was data modeling, which I hadn't really touched upon too much because that would have been a bit of distraction, and this is not a data talk. So data modeling was one thing that helped us achieve this. Yes, we had this opportunity of having independent data sets, but because we had created a very clean data model, it helped us to not write too much bespoke code and handle things differently for different data sets and so forth. And then finally, small functions promote reuse. So that was the point I was making earlier, that by the time we finished our third pipeline, we could organically see very clearly which of these functions can be lifted out into a core library. And we didn't really have to spend too much time to do that because our entire approach was to create these whole pipeline into form of small functions, which just made it easy to lift them with their tests and move into a core library, fix them in one place. If there were bugs, release a new version, and all your pipelines just get that new version. And that's mostly my talk. And thank you to all the members of ZIVOs and the organizing team for providing the opportunity to present on this stage and also managing a conference at this scale. Thank you.